Hi, welcome to the fourth session on group theory. So we will recall the definition of groups and look at lots of examples. Okay, and there will not be much of theory except a lot of examples. Okay, right, let's screen share. Yeah, so let us recall. Yeah, so G is a set on which there is a binary operation which is also associative. Okay, then we call it a semi group. If it also has identity, okay, identity, then we call it the monoid. And if A and G, for if A given this, okay, there is a B in G such that AB equal to 1 equal to BA, which is also E, then we call A invertible or A unit, right? Therefore, a monoid is a group if every element is a unit. It's a unit. Okay. So the standard definition will be, okay, let G be a set. Usually they will say non-empty because your teacher may not like if you don't write non-empty, but that's a superfluous because we are going to say there is an element called identity, right? So that with what property? There is a binary operation star from G cross G to G, and two, the binary operation is associative. Okay, I do not recall the definition. We had been using it for last 3 times. Then there exists one or E in G. There exists an element in G. Therefore, I do not assume it's non-empty. It's going to come like this. There is an element in G, so that for every G in G, G star E equal to G equal to E star G. Hereafter, we will write only star of AB. Instead of writing A star B, we will write it as only AB. Okay. The next fourth element is for every A in G, there exists a B in G, so that AB equal to identity equal to BA. Is that okay? And we had already proved lot of things. Okay, these are the facts by now. Okay, associativity implies, okay, implies generalized associativity. I don't want to say what it is. Okay, and second, the identity element is unique. Unique, and for every A in G, there is a unique B in G, so that AB equal to TB. So this B is unique and denoted by A inverse. Call it the inverse of A. Okay, these are the facts which you already know. Now let us look at lot of examples. The first example is, of course, integers under addition. Okay, this is a group. We had already seen all those things. And for similar reason, if I take set of rationals under this is also a group under addition, and set of real numbers under this is a group, and the set of complex numbers under this is a group. Okay, and all these groups are, a group is abelian if the binary operation is commutative. This is abelian. A B E L I A N. Commutative. That is, for every A and B in G, the product AB should be the same as the product BA. We call it a product, group product. Okay. So all the examples in this list are commutative, abelian, right? And the next example is also abelian. Let us look at all n cross n real matrices. If you want, take it to be 2, but that's not necessary. Under addition, this is also an abelian group. Right? Now let's look at the third example. In the complex numbers, look at the set G, which consists of plus or minus 1 and plus or minus I. And the group operation star is the complex multiplication of complex numbers. Multiplication of complex numbers. Okay, therefore we know that, for example, I times I is minus 1 and 1 times I is I, minus 1 times I is minus I, and I, okay, is there anything else? Minus I times I is 1, because this is minus I squared, but by definition I squared is 1, therefore it's, right, this is, let me write, this is minus of I squared, but that is minus of minus 1, therefore it's plus 1. Okay, so since multiplication of complex numbers is commutative, okay, complex multiplication is commutative and associative. Therefore G is a group, okay, with 1 as identity. What is the inverse of I? Inverse of I is minus I, because we saw its product is 1. What is the inverse of minus 1? This inverse is 1. I inverse is minus I. Okay. So we have got a group, right? Okay. Now these are the things first. Now let's look at a general way of looking at. I said there is no theory, but I will do that. Suppose M is a monoid. Remember, monoid is a binary operation, associative, and exists of identity, right? And let G be the set of elements A in M such that A is a unit. What does it mean? A has an inverse. Right? This set is non-empty. Why? Because we had already seen 1.1 is 1 or E dot E EC, because it's an identity. Right? Therefore 1 belongs to G. Therefore this is non-empty. Right? Okay. Now I claim the G with respect to monoid has an operation, right? Call it star, which as usual we will not ignore. Restrict that to only G. This is a group. Okay, this requires bit of understanding. Let us go slow. What we do is, suppose I have A and B in G, then A star B is AB. I have to say it is in G, because I want to restrict G, which was defined from M cross M to M. We want to restrict it to G cross G to G. So you have two elements A and B. I have AB, that will be an element in M, but I want it to be an element in G. But we had already seen, if A and B are units, then AB is a unit. Is that clear to you? Right. And why is it associative? Because the star operation is already associative in the monoid case. and the inverse exists, sorry, identity exists and inverse also exists, right? Therefore G star is a group. Okay, understand this, go slow, pause, review, proceed. P or P. And if in case you have already learned some group theory and think of something like subgroup etc., don't. Okay, M is not a group at present, it's only a monoid. Okay, if it's a group, then all elements are units and therefore G will be equal to M, right? So it's not. So the point I have to say is look at only the units, then take any two units and define the product A star B. We already know it's a unit, we have seen it, right? Identity belongs to that. And the star operation is associative. If A, B, C are there, A dot B within bracket, after that dot C is same as A dot within bracket B dot C. That is already seen, right? Therefore it becomes a group. You understand this? Right. Now comes a very interesting thing. Hence, let us look at, suppose I have Q, right, under multiplication. Okay. So this is a binary operation. This is a multiplication. Right? So this is, and this is a monoid. Why? Because one here, one rational number, that is an identity. And multiplication of numbers is associative. So it's actually commutative also here. Anyway, yeah. But now when does it have a unit? If I have a rational number R, okay, then I want to know whether R is there, whether there exists an S, whether R is equal to 1. When does it happen? If and only if R is not equal to 0, right? If R is in lowest term P by Q, we already saw S equal to Q by P, right? Therefore, in this monoid, look at the units. Units are going to be non-zero. So let Q star denote the non-zero rational numbers. Then Q star under multiplication is a group. Because in the monoid, there is a monoid, I am collecting all the units. You understand this? Do you like this example? Now we can do for everything. For real numbers R under multiplication, that's a monoid, and take all non-zero real numbers. Okay, that is, call it R star. R star with multiplication is again a group. And similarly C star, right? C star is what? All non-zero complex number under multiplication. That is also a thing, right? But can you think of something much more interesting? Because if you notice, all these things we have seen are all commutative. They are all abelian. All the binary operations are abelian, right? So I want something non-abelian. I am sure all of you got it. What are you looking for? You know, matrix product is non-commutative. Therefore, you have to look at it. Yeah? So let us do that. So now let us look at all n by n square matrices with matrix multiplication. Star is matrix multiplication. So you know this matrix multiplications. Okay, this is a binary operation and it is associative. This you must have seen in your matrix algebra course, right? And it's also a monoid because identity matrix. Okay, n cross n identity matrix that serves as an identity because yes, identity same as A is same as identity A for every A in MNR. Therefore, MNR is a star is a non-commutative, non-abelian monoid. Okay, it's a monoid. That's more important. Now, what are the units here with respect? If given A in MNR, what I am looking for, I want to know that there is a B said that A times B is identity. But from a matrix algebra, you know that is same as saying A is invertible. Okay, A in M and R is a unit if and only if A as a matrix is invertible. Is that all right? Okay, right. Therefore, let us look at the invertible matrices denoted by GL and R. These that are used. This is called general linear group. Okay, this is a set of all A in M and R. Okay, where A is invertible. Okay, right. So, with analogy, let me call it M and R star. Remember, for Q we had a Q star, that is all units, and for R we have R star, which are all units. For C we had a C star, and for M and R, these are the units. M and star, M and R star, that is the units. That is all invertible, right? So, we know this is a group. Sorry, there was a phone call which I had to attend. Let me see. So, this becomes a group. Okay? Try to understand what we did here. Okay? I am going to make use of this again. You see that very simple principle gave us lot of groups now. Whenever I have a monoid, look at the group of units or group of invertible elements, that becomes a group. If the monoid is commutative, then the group is abelian group because the binary operation continues to be commutative. Yeah? Isn't it a good example? Very good. Now I want to introduce one of my favorite examples. This is what I call ax plus b group. Okay? That is, for every a in R star, that is non-zero real, and b in R, this is non-zero real. Okay, this is anything, right? We look at the map AB from R to R. How do I define? F of AB of x equal to ax plus b. Sorry for interruption. I will stop this example. There is one more interesting example. How to get a group out of a monoid. Okay, I forgot. We already got a non-abelian thing, right? I want to get one more non-abelian thing. Can you guess where it should be? Remember, we have seen if S is a non-empty set, if we look at all maps from S to S, then it is a monoid. Identity map being the identity, and the operation being composition of maps, right? That's a monoid. We have seen it. It's non-commutative. Also, we have seen the moment it has two elements is non-commutative, right? Now, what I am looking for in this monoid, I want to understand which elements are invertible, which are units. We had already seen it in one of the earlier videos, but let's again do that. Okay. So, are you excited? One simple thing, it generates lot of examples. Okay. See, algebra in general mathematics, that is the idea. You look at various examples, see the pattern, and try to make it a general principle, general theorem, or general lemma. That's what we are doing. Okay, let's go to that. So, we will pause. We will resume later. Okay, now come back. So, let S be a non-empty set. Okay, let us look at the monoid M, which is set of all functions from S to S, all maps. all maps, right? And what is the operation? Star is the composition of maps, right? And what is the identity? Identity is the identity. Eh, okay, I is nothing other than is a map from S to S, so that I of x equal to x for all x in S. Okay, so we know this is, therefore the M is a monoid. Now I want to know when an element F in M is a unit or is invertible. I don't want to use invertible because you will see the reason. Okay, invertible in the sense of monoid, but we ought to look at something. It's a unit if there exists a G in M, that is another map from S to S, such that G composite F must be equal to identity, that is also equal to identity. G F composite G is also identity. Is that clear? This is a group operation. But then from set theory, you know this is same as saying F is a bijection and G is the inverse of the bijection, inverse map of F. Okay, if you are don't if you are not sure, look at my foundation videos or our book on foundation, Ajit Kumar, Baba Sharma and Kumarism, a foundation course in mathematics. Okay, therefore the if M is the monoid, this G is nothing other than set of all F from S to S, such that F is a bijection. If it is a bijection, the inverse exists. Okay, is that clear? Therefore, this G is again in general non-negative, non-commutative, non-abelian. Okay, but it's a bijection, then we need the assumption to be S should have at least 3 elements. Because if S has 2 elements, okay, the bijection will be x1, x2. Therefore, the first one will be going to identity. x1 goes to x1, x2 goes to x2. The other one will be x1 goes to x2 and x2 goes to x1. Only there are 2 elements, right? And you can check, okay, this is identity, this is the one map. These are the only 2 elements, therefore they always commute. You understand that? But if it has 3 elements, then in general it's not commutative. Suppose I have 3 elements, x1, x2, x3, right? So let us look at F, which maps x1 to x2 and x2 to x. I do not know, but let us just see x2 to x3. And G to be x1 to x3, and therefore it's a bijection, therefore x3 we must go to x1. Yeah, in fact I don't need, I think it should be transposition should work. F of x1 goes to x2, x2 goes to x1 and x3 goes to x3. And G is x1 goes to x1, x2 goes to x3 and x3 goes to x2, right? These are all bijections, right? And if there are more elements, if x is not equal to x1, x2, x3, then define f of x to be x and g of x to be x. Okay, but at present concentrate when S has 3 elements, right? Now let's look at what happens if G composite of x1. So x1 goes to x1 under G, under F it goes to x2, right? This is f of G of x1 is x1, but that is x2. Let us look at what is G composite f of x2. Sorry, yeah, G composite f of x2. F of x2 is x1 right? And g of x1 is x1, right? Therefore, f composite g is not equal to g composite f, right? Remember, when two functions are not equal, if I can find one element in the domain such that the values of these two functions at that point are different. That's what you got. At the point x1, we found it is different, right? F composite g of x1 is x2, whereas g composite x1, okay, this is x1, is x1, g of x1, g of x, okay, f of x1 is x2, right? F of x1 is x2, and therefore g of x2 is what I am looking at. Yeah, g of x2 is x3, sorry. Okay, am I confusing? What g of f composite g, this is f of g of x1, g of x1 is x1, therefore, and f of x1 is x2. Whereas g composite f of x1 will be f of x1 is x2 and g of x2 is x3, right? Therefore, they are different. So, what have we shown now? Here, if I take a non-empty set as, look at all bijections, okay, then that forms a group. And that group in general is non-commutative, not abelian. The moment the underlying set S has at least 3 elements. Is that proof clear? I proved it for 3. For other x not equal to x1, x2, x3, you define f of x equal to x, g of x equal to x. Therefore, you can check. We had already done it in the case of all maps. Okay, the same proof works here also. Right? Is that clear to you? Very good. So now again you see the advantage. The moment I have a monoid, I look at all units in that. Okay, then the set of units in a monoid form a group. Beautiful. We got a lot of examples, right? Okay. Now we can go back to our ax plus b group. So return to ax plus b. Okay. So for any a in R star and b in R, you look at the map f of a comma b as a map from R to R. So f of a comma b at x equal to ax plus b. You can see this is a bijection. Why? Because if you give me any c, okay, I want to know whether it is 1 1 on 2. First it's on 2, okay. Let us say 1 1 ax plus b1 equal to ax plus b, that is f of ab, x1 equal to f of ab x2, okay, if and only if this happens, right? But this happens if only if x1 equal to x2, and this happens if only if multiply both, since a is non-zero, multiply by 1 by a on both sides, 1 by a times ax1 equal to 1 by a times ax2, okay, that implies x1 equal to, if and only if x1 equal to x2. Therefore, these maps are 1 1. Are they on to? Why? Suppose I have ax plus b, okay, and c is any real number. Can I solve for this? Does there exist an x such that this happens? Yes, because ax equal to c minus b, and since a is invertible, I can write 1 by a to c minus b, right? There, take x equal to this, therefore a into 1 by a into c minus b plus b. Okay, this is c minus, okay, this happens 1 by a and cancel, therefore c minus b plus b, which is c. I got it. So all these maps are bijections, right? And okay, now therefore I can compose. What do I mean by this? Suppose c is again r0, sorry, non-zero, d is a real number, then I want to compose these two things. Okay, since they are invertible, it should also be invertible. But what I want to say is something much more. It's not only invertible, it is again of the form f of alpha beta, where alpha is in R0 and beta is in R. I want to claim this. Do you understand this? Yeah. See, f of AB is a bijection and f of CD is also a bijection. Therefore, composition will be a bijection. No problem. Bijection of R to R, right? Bijection of R. But I want to say it is again of the same type. It is f of alpha beta for some non-zero alpha and some beta. Do you understand this? Okay, it is a very trivial checking. We'll do it. So let us look at. So f of CD composite f of AB. This acting on a real number x by definition f of CD acting on f of AB acting on x. But what is this? This is f of C comma D acting on ax plus b. So this is the real number you are looking at. F of CD has to act on that. How will it act? It will act C times ax plus b plus d. Do you understand this? But this is algebra now. I can write this a times c or c times ax plus bc plus d. Okay. Now remember, a is non-zero, c is non-zero, and we know that's a group. Therefore, a is non-zero. That is my alpha. And what is my beta? This is my beta. Therefore, it's alpha x plus beta. Okay. Pause. Review. Proceed. So we proved that, right? So under composition, okay, the ax plus b I have not denoted, so let me call it a name. Okay, then I will say that forms a group. The set of all maps of the form f of ab, where a is non-zero, b is a real number, a is a non-zero real number. Under composition, okay, it remains it's a okay, it's a binary. The composition is a binary operation on the set. Is that clear? Do you understand what I'm saying? Okay, let me go back, do that. So the composition from, let us look at, give a name. Okay, this is called affine group of R. Let me write AF of R, affine group. Don't worry about the word affine group of R, call it simply G. Okay, the composition from G cross G. Okay, if I have f of a CD and f of AB, then it becomes go to f of AC and BC plus D. Is that okay? Right. Now I already showed what is the inverse. Remember, I wanted to say this. We already found what there should be the inverse. X must be this. Okay. So what should be the inverse of f of AB? Okay. So now you see the reason why one should go through foundation course. I do not know how many of the second year BSc students will be able to find the inverse of this map. Okay, these examples are not usually done in even at MSc level most often. Okay, unless you're okay, right. So don't worry about, but go through these examples. Don't worry about your exam. Okay, go through these examples. You will be become very comfortable with algebra and very abstract thinking also. Right? Are you following me? So what is the point I want to say? We have seen this affine group, namely ax plus b group. It's closed under composition. Very good. Now I want to know what is whether it's a composition is associative, therefore there is no problem. Now what is the identity? Since it's a bijection, okay, the identity must be the identity map of R, right? X plus b is what? Bijection of R. Therefore, what should be the identity under for bijection? Identity map of R. Okay, that's fine. Can we get it that way? That's in the first question. Second question is what is the inverse? What is the first question? Identity map should belong to Ax plus B group. That means I have to say if identity map belong to that, what is A and what is B. Do you follow that? So let us do that. That's very easy. So before that, let us look at if I take what is the f of a b of x, I want to be x. What does that mean? But I know this is ax plus b. So ax plus b, x must be x. That means b must be 0 and a must be 1. Do you understand that? Therefore, f of 1 comma 0 is nothing other than the identity map of R. Therefore, that identity map of R belongs to G because it's of the form f of 1 0. Please understand, this is a subtle point. These are the things which will make you happy with abstract thinking, right? Identity, for bijections, identity map is the identity for the binary operation. But we want to say we are looking at ax plus b group. Therefore, my identity map should be an element of the ax plus b group. That means I have to find what is a, what is b. Have I done it? Yes. A is 1, b is 0. Okay, very good. Next, I have to find what is the inverse. So, if I have f of, let us do that. We are already done. F of cd composite f of ab. I want it to be identity. F of 1 comma 0. Right? But this we had already done. This is f of, therefore this is at x equal to this at x is equal to x. But what is this? Do you remember? It is acx plus bc plus d. You understand? This must be equal to x. Please understand. I want to know what is the inverse. Okay? What is the inverse? F of ab inverse. Okay? So it must be, I want to say it is again in the group G. Okay, that means it must be of the form some f of c comma d. Therefore I have to find out what are c and d. Okay, so let us assume f of c d compose f of a b of x equal to x. That means ac x plus bc plus d must be x. So what does this mean? This happens if only you ac must be 1, bc plus d must be 0. What are unknowns? C and d. Therefore c must be 1 by a. We found out. And what must be d? D must be minus bc. Yeah. So f of ab inverse is f of a inverse, that is 1 by a minus bc. I hope I wrote it correctly. Is it bc plus d? I should not make any mistake. Yeah, bc plus d, right? Okay. Therefore my d must be minus bc. Yeah, right. Is this clear? Well, you proceed. And composition of maps is associative, therefore it's associative. So what I have done? So this affine group G, let me call it ax plus b group. It will be easier to say. Okay, is a monoid and it's a group. Okay, pause, review, proceed. I hope I did everything here. Okay, please go through that. As I said, these exams are not done, but don't lose heart. Go. So the advantage of this thing, you will see that indirectly I am reviewing the foundation also for you. Okay, and also trying to teach some other abstract, subtle logic. Okay, so bear with me. Go through this. You will begin to enjoy abstract mathematics in general, algebra in particular. Okay, don't give up. Okay, right. Now let's do. And this is non-abelian. You can see that. Okay, why? Because f of cd composite f of ab, we saw it is f of ac plus bc plus d, if I remember right. So interchange them. f of AB come with f of CD will be what? Okay, that is same AZ. Okay, this will be the same thing AC or CA. But then what happened? You take this B and this C. Therefore, I have to take this D and this A. Therefore, it's going to be AD plus. And then what do? I take this D. Therefore, that is B. Okay, right? So, and these two functions, okay, are they equal? Now we want to know that they are equal. Question mark is whether they are equal. Okay, if they are equal, that means these two functions must be the same. But what is the value of those functions at x? F of AC. Okay, let me write. So at x, what is the value of this? This is ACX plus BC plus D. At x, this is ACX and then AD plus B. Okay, so ACX, ACX are equal. Therefore, I should have BC plus D must be equal to AD plus B for all choice of A and C non-zero real numbers and B and D, this must be true, right? So you can just take arbitrary thing. For example, let me take A equal to 2 and C equal to 3, right? Let us do that. And B equal to 1 and D equal to minus 1. Just something arbitrary. Therefore, what is BC? BC is going to be 3 plus D is going to be minus 1. Therefore, it is equal to 2. What is this? AD? A is 2, D is minus 1, therefore minus 2, plus B is 1, therefore it is minus 1. Whereas this is 2. So they are different. Is that clear? Just for fun, just so that you know, you should not hesitate. You should think like a child. There is some toy, you don't want to read the manual. No child wants to read a manual, right? It begins to operate. So play with it. Play with that object. Same way I am playing with that. Okay. In fact, you should be doing. At my age, I am playing with it. Okay. Please do that. Okay. Therefore, this ax plus b, the set of maps f of ab, where a is in R0 and b is in R, under composition is a non-abelian. Non-abelian meaning the binary operation is not commuted, non-abelian group. Okay. Now let us look at a different avatar of ax plus b. Right? Let me look at the set of elements of the matrices A, B, 0, 1, where A is non-zero and B is the real number. And the star is matrix multiplication. Right? Therefore, what happens if I take CD 0, 1 and AB 0, 1? What is the product? The product is CD times A0, that is CA, and CD times this one, first row by second column, that is BZ plus D, and this 0, 1 times, okay, this row 0, 1 and multiply with the column A0, that is going to be 0, and this row and this column, that will be 0, 1, 1. You see that? So this is okay. Therefore, matrix multiplication star is a binary operation. right? Take any two elements here and take their matrix product, it is again an element. Remember, A is non-zero, C is non-zero, therefore this is non-zero. But much more interesting, okay, and matrix multiplication is associative, and the identity, what will be the identity element? Identity element will be 1 0 0 1. Is it of the same form? Right? A is must be non-zero, B must be any real number, and 1 should come here. So I got it. That also belongs to G. Right? Okay. And is it invertible? Yes. Because what do I want? If you give me A, B, 0, 1, I want to find a C and D, this another matrix, such that this must become 1 0 0 1. Okay, that means CA must be 1, that means C must be 1 by A, right? And next BC plus D must be 0. What is unknown? Unknown is D, therefore D is minus BC, right? Therefore inverse also exists. A, B, 0 1 inverse is A inverse minus B, BC. But what is BC? B by A. Yeah, that is what I was missing. See, do you remember every time I was saying what is this C? I forgot here. Okay, this is 1 by A. Okay, right. Now let's look at what I want. So we can see, look at the earlier, compare these two examples. Ax plus B group and this AB01, A in R star, B in R group. Okay. Now any element here is of the form f of AB, but f is completely determined by A and B, where A is in R0 and B is in R, and this also the same. So you can see f of AB going to this matrix AB01, this is a bijection of these two groups. Also look at the multiplication f of CD composed f of AB. Okay, where does it go to? It goes to the matrix multiplication of CD01 times AB01, right? CD goes to this matrix, AB goes to this matrix, the product also goes to, that is the composition of this goes to the product of these two matrices. Okay, and this is the bijection. So those of you who learn something more about group theory, you should jump at it now, right? You know, you understand what is happening. Yeah, right? Very good. I think this is a very good time for me to stop. Please go through these examples, and my advice is the same. Do not jump. At every pass, PRP, stop it, review it, try to understand as much as possible. Okay? And if you keep revising, you will see that you become very, very comfortable with abstract way of thinking. And if you are afraid of group theory, you came to me, you will find that mine seems to be more difficult than what you have seen in textbooks or your class notes. Okay? But mine is somewhat more holistic. Okay? I want to prepare you with the foundations and little more abstract thinking. That is why I tried to do all those things slowly with all details. I hope you appreciate this. Stay with me, and after a few more videos, you will be very, very confident of group theory. Okay? See you soon.